The Wheeler-DeWitt equation is central to the problem of time. Page-Wootters is a serious proposal where time appears through quantum correlations. Rovelli's thermal time idea treats time as emerging from thermodynamic state rather than being put in from outside. But there is still a problem. Even if the Page and Wootters idea shows how time might emerge from quantum correlations, it does not explain everything we mean by time. It gives us a way to understand how one part of the universe can act as a clock for another part, but it does not automatically explain why time has a direction, why entropy increases, or why memories point towards the past and not the future. This means quantum mechanics may help us understand how time appears, but it may not, by itself, explain the full human experience of time. A clock can tell us that one state comes before another, but it does not explain why broken glass does not return to the table, why smoke does not gather back into a cigarette, or why our minds remember childhood rather than old age before it happens. This is where Carlo Rovelli's ideas become useful. Rovelli has argued that time may not be a universal background flowing everywhere, but something that appears when systems interact and exchange information. In ordinary life, this feels strange because we are used to thinking of time as the thing inside which everything happens. But perhaps that is backwards. Perhaps there is no master time outside the universe. Perhaps there are only physical systems changing in relation to one another. One system can behave like a clock only because another system can be compared with it. If nothing interacted, if nothing exchanged energy, if nothing recorded anything else, then perhaps there would be no meaningful time at all. Rovelli and others have also explored what is called the thermal time idea. The basic suggestion is that the flow of time may depend on the physical state of a system, especially its thermodynamic state. That sounds abstract, but the underlying idea is fairly simple. We usually imagine that time exists first, and then heat, energy, motion, and entropy unfold within it. The thermal time idea asks whether it might be the other way around. Perhaps the state of the universe itself gives rise to the time we observe. Perhaps time is not painted onto reality from outside, but grows out of the way matter, energy, and information are arranged within reality. This links back to the arrow of time. In episode 26, we saw that entropy gives time its direction. In episode 27, we asked why the universe began in such a special low entropy condition. Now quantum mechanics adds another layer. If time can emerge from correlations between systems, and if the direction of time is connected to entropy, then perhaps time is not one single thing at all. Perhaps what we call time is made from several ingredients: change, comparison, memory entropy, information, and quantum relationship. Remove those ingredients, and the familiar thing we call time may disappear. This is why quantum mechanics does not simply contradict what we have already said. It deepens it. In episode 29, we asked whether time really exists. We wondered whether clocks measure time or merely compare change. In this episode, quantum mechanics suggests that comparison may not be a weakness in our thinking. It may be the key. Perhaps there is no such thing as time for the universe as a whole, because there is nothing outside the universe against which it can be compared. But inside the universe, one part can change relative to another part. One system can act as a clock. Another system can appear to evolve. From inside, time exists. From the deepest outside view, if such a view even makes sense, the whole universe may be timeless. This sounds almost impossible, but we have already met similar ideas. In relativity, there is no universal now. Yet each observer still has their own present moment. Near a black hole, time can almost stop for a distant observer, while the falling astronaut experiences their own watch ticking normally. For a photon, no proper time accumulates along its path, yet to us light can take billions of years to cross the cosmos. Again and again, physics has shown us that time is not one simple universal river. It depends on viewpoint, motion, gravity, entropy, and perhaps quantum correlation. Quantum mechanics also introduces the idea of measurement. Before a quantum system is measured, it may be described as containing several possible outcomes. After measurement, only one outcome is observed. This has led some people to wonder whether measurement itself helps create the flow of time. We must be careful here, because this is interpretation rather than settled fact. It would be wrong to say that human consciousness literally creates the universe by looking at it. But measurement, interaction, and information are undeniably central to quantum theory. The world we experience is a world of definite records. A detector clicks, a photograph is formed, a memory is stored, a particle leaves a track. These records give us history. Without records, there may be no meaningful past. Decoherence is another important idea. In quantum physics, tiny systems can exist in delicate combinations of possibilities. But when they interact with their surroundings, those possibilities rapidly become entangled with the wider environment. The result is that the world begins to look classical and definite. A chair appears to be in one place rather than many possible places. A cat appears alive or dead, not both in any practical sense. Decoherence does not solve every mystery of quantum mechanics, but it helps explain why the strange quantum world gives rise to the solid ordinary world we inhabit. It may also help explain why time seems irreversible, because once information has leaked into the environment, reversing the process becomes almost impossible. That matters for our question because our sense of time depends on records. A footprint is a record of a past step. A fossil is a record of a past organism. A memory is a record inside a brain. A detector mark is a record of a quantum event. These records are not floating in some separate river called time. They are physical arrangements of matter and energy. They exist because interactions have happened and left traces. Perhaps the past is simply the collection of records that exist now, while the future is the set of possibilities that have not yet become records. This brings us back to the deepest problem. If the whole universe is described quantum mechanically, who or what observes it? In a laboratory, we can speak of a scientist measuring a particle with an instrument. But if the system is the entire universe, there is no outside scientist and no external measuring device. The universe must somehow contain its own observers, its own clocks, and its own records. That is why the problem of time is so difficult. We are not watching the universe from the outside. We are inside it, made from the same matter, governed by the same laws, and using internal processes to measure other internal processes. Perhaps this is why time is so hard to define. We are trying to describe the very thing that makes description possible. Every sentence we speak unfolds in time. Every thought we have seems to move from one moment to another. Every experiment requires before and after. Yet the deeper physics goes, the less obvious time becomes. In Newton's world, time was simply there. In Einstein's world, time became flexible. In quantum gravity, time may disappear from the fundamental description and then reappear only when parts of the universe are compared. So does quantum mechanics create time? The honest answer is that we do not yet know. It may be better to say that quantum mechanics gives us serious reasons to believe that time could emerge from something deeper. It may emerge from entanglement, enact from correlations, from records, from thermodynamic conditions, or from information itself. None of these ideas is yet the final answer, but they all point in the same unsettling direction. Time may not be the background stage on which the universe performs. Time may be part of the performance, and that is a remarkable reversal. For most of human history, time seemed more certain than almost anything else. The sun rose, the seasons changed, people aged, and clocks ticked. Time was the thing we trusted when everything else changed. But modern physics has steadily taken that certainty away. Relativity showed that time is not universal. Entropy showed that time has a direction only because the universe began in a special state. Quantum mechanics now suggests that time may not even be present in the deepest description of reality, but may arise from relationships within the universe itself. If this is true, then time may be less like a river and more like a pattern. A river exists whether or not anyone watches it. A pattern exists only through relationships between its parts. Remove the relationships and the pattern disappears. Perhaps time is the pattern formed when matter changes, information spreads, entropy increases, and quantum systems become correlated. We experience that pattern from the inside and call it the passage of time. This does not mean time is unreal in an everyday sense. Pain is real. Aging is real. Memory is real. The ticking of a clock is real. The difference between yesterday and tomorrow is real to creatures like us. But something can be real without being fundamental. Temperature is real, but it emerges from the motion of particles. A wave is real, but it emerges from the collective motion of water. Perhaps time is similar. Perhaps it is real as an experience and as a physical description, but not fundamental at the deepest level. That may be the most careful conclusion we can reach. Quantum mechanics does not prove that it creates time. It does not give us a neat final answer, but it opens the door to a profound possibility. A timeless universe may contain time for those living inside it. From the outside, reality may be a complete quantum structure. From the inside, because we are part of that structure, we see change, memory, order, disorder, and sequence. We call that sequence time. Thank you for watching or listening. If you enjoyed this episode, please like and subscribe. It really helps the channel and lets me know you'd like more episodes exploring the mysteries of time. And if the next episode is already on your screen, just click on it now and we'll continue discovering time together.